All right, so does anyone have any questions about anything? Okay, let me get the whiteboard set up, and then we can do a quick review of where we were last time and what we're doing going forward. Okay, I'm getting there. I hope. Okay, good. So let's see. Last time we were talking about motion in a circle. So we have something moving in a circle with velocity v. We really specifically focus on moving in a circle at a constant speed. What we saw is that this is related to the situation where the acceleration vector points toward the center of the circle. And we worked out a formula for the magnitude of this thing. This is known as centripetal acceleration. And our formula for centripetal acceleration was a centripetal equals v squared over r. I'm going to tell you, I'm a little sloppy when I get to this unit on whether I use a small r or a big R. I'm not doing that like to indicate some difference. The letter R is the radius of the circle. Sometimes, yeah, Tommy, question.
I'm sorry, I pushed the wrong button. Sorry.
Oh, okay. No problem. It happens. So sometimes, I mean, I try to use the little r in the equation, and then in a problem, capital R is often the radius of the particular circle that's going on in the problem. But I'm not sure I'm totally consistent with that, and I'm not sure that the textbook will be totally consistent with that. So, I mean, of course, ask if you ever have a question if it's unclear, but generally, R is just the radius, and I may use a big R, a little r inconsistently, but I'll try to stick with what I just said. So if the object is not moving at a constant speed, suppose it's moving kind of 10 meters per second, and a little bit later its velocity final is 20 meters per second. So what that means is that the net force, instead of just pointing toward the center, it kind of points forward a little bit, so that we would split it up into a net force centripetal component and a net force, what we would call tangential, which means the piece of the force that's in the direction of motion. So all semester before last class, whenever we talked about net force, we're always just doing this piece. And now we recognize that if there's a piece of the net force that's perpendicular to our motion, it's going to cause us to curve. But this piece will still cause us to speed up or slow down. So we have a centripetal force that is, it could be friction, it could be tension, it could be gravity, it could be normal force, it could be applied, it could be anything, or any combination of forces. And then we have any remaining forces, whatever doesn't point toward the center, that becomes, tangential. And then we could also have a little bit of net force in like the y direction. But that would be unusual because that car would jump off of the road. So ordinarily, this one's going to be 0. And in our problems, we're really not going to have this. I mean, almost not at all. But I'm just kind of mentioning it for conceptual sake. If you're wondering, well, how do you speed up or slow down? Well, you still have to curve, so you have to have a piece of your force going toward the center of the circle, but then you need a little piece of the force that's in the forward direction to speed up, or in the backward direction if you wanted to slow down. So last time we talked about a car going around a circular track and using friction to keep on the track. And so we said we have, net force, let me make that black. So we had the net force centripetal equals m times a centripetal. And in that case, we had only friction. And I didn't really talk about the sign of the components when we talk centripetal, because when we're talking y components, up is positive, down is negative. When we're talking x components, right is positive, left is negative. What about centripetal? Well, if it points toward the center, we give it a plus sign. If it points away from the center, we give it a minus sign. So we'll see some examples of those two cases today. But I just kind of swept that under the rug last time, didn't mention why I called the friction positive there. And we know that the friction is mu times normal. And, I think probably the reason I sometimes move to large R is because my V's and my R's look kind of similar. So sometimes I do that. Now, remember normal force, if we're on a flat area, we're going to have normal force up and force of gravity down, and they have to cancel. So we had mu times m times g equals mv squared over r. And our m's canceled, and we wound up with a few algebra steps, v being square root of, mu times r times g. And if we have a real problem, we might label that r as capital R or something, and then this might become that capital R, okay? But that's what we did last time. And we saw that if the coefficient of friction goes down, the radius has to go up to make this balance. And if the coefficient of friction and g stay the same, but we speed up, then r has to get bigger. And so we kind of are trying to build some intuition on that. And we're going to continue doing more problems today in that vein. So today I want to start with, I want to imagine, hold on one second. Oops, I kind of messed this up a little bit, so just give me 1 second. This is just has to do with the software I'm using. There we go. So suppose we have a car going around a track, but the car is on a banked curve. So that means the road is slanted, and it kind of, it's kind of like a racetrack, like Indy 500 or something. Okay, so there's this circular track, and we have a car that is on the road, and it's kind of coming out of the board at us. There's the grille, and there's the window, and the steering wheel. Okay, so this car, I mean, it's not a really nice looking car. Probably this is like $100 car. Okay. Anyway, it's going around the track, and the track has, some radius. And what I'd like to do is I'd like to figure out a formula for the velocity that the car can go around this track without friction. Okay, and I'm only doing that to make it simple. Then after we see how that works, we'll add friction in. But imagine that we had no friction. So this could be, in real life scenario, this could be some event in the Winter Olympics with like the luge or something, where you have this sort of sled going through these channels and curving around, but there's really no friction, but somehow it still curves. How is that possible? Well, we have to look at the forces acting on the car, and in this case, there's going to be normal force and force of gravity. So we've seen a picture like this before, and the difference, the difference between this and our previous inclined plane problems is that the acceleration vector does not now point down the ramp, it points toward the center of the circle. You have to imagine that this car is traveling in a horizontal circle. Okay, so maybe the center's more like that. But it's traveling in space in a horizontal circle. Even though the road slopes down, the car doesn't go up or down. It just goes in this circle. And so when we're breaking things into components, we do not want to tilt the picture or tilt the paper, tilt our head, whatever way you think of that, because the acceleration vector does not point down the ramp. It actually points, toward the center of the circle, which is the regular x direction. So in this case, we would split the normal force into an ny and an nc. Okay, so I'm not calling it x, it's c, because I might have the same picture on the other side, and then it's pointing to the left. It doesn't matter left or right, it matters toward the center or away from the center. So we're still doing the same thing that many of you, did very well on the last contest. We are drawing a picture, we're drawing the forces in, we're splitting the forces into components, and we're writing down net force equals ma, and we're going to split this into components. It's just that instead of x and y, now it's going to be c and y. That's it. Only change. And what we're trying to do is we're trying to find how fast the car goes around this track if it's at a certain angle. And we'll try to interpret the result when we get at the end. We're going to get a formula here because we're not using numbers. And then that formula is actually going to be worthwhile to kind of keep hanging around for a little while. So the only force that has a centripetal component is the normal force. We have N centripetal equals M times A centripetal. And it gets a plus sign because it's pointing to the right. Okay, the normal force is leaning inward a little bit. In the y direction, we're going to have ny minus fg equals m times ay. But like usual, we are trying to figure out how this car can stay on the track without jumping off the track. So there's no acceleration in the y direction. Now, the normal force centripetal component, the normal force, remember, is the hypotenuse. And there's an angle up here. And whatever that angle is, I'm going to show you in a minute that it happens to be the same as this angle theta. So that's probably easy to believe. They look similar. I'll prove that to you in a few minutes. But the centripetal component is opposite to that angle. So we're going to have n times the sine of theta equals m times v squared over r. Okay? So I can just leave the r underneath the whole thing. But to find the normal force, as usual. Now, I would say 2/3 of you did an excellent job with this on the contest, with finding the normal force. And the other third seemed to just try to be operating on memory, trying to memorize what the normal force was sometimes with a picture that looked kind of like that. And in other words, we're making guesses, and that's not good. The normal force really depends on the situation, and we don't want to memorize a ton of cases. I mean, that's a losing strategy for this class, especially considering that we need to know this stuff not just on the last contest, but we need to know it on the next contest, and we need to know it going forward. And so there's more and more cases to memorize. It just becomes impossible. So we want to solve for the normal force. Now in this case, we would have ny equals force of gravity, and ny, if I look at the picture, it is adjacent to that angle. So we're going to have n times the cosine of theta equals mg, and n will be mg over the cosine of theta. So this is a totally different normal force than anything we've seen before. When we had a regular inclined plane, you might remember, if you're one of the ones kind of memorizing stuff, that the normal force was mg times cosine of theta. Now it's mg divided by cosine of theta. So it really changes case by case. So we take this, but our strategy doesn't change. That's why we want to work with a strategy instead of memorizing stuff, because the strategy will be the same every time. Now we replace the normal force with our expression. And we can see now that the mass is going to cancel out. And if we wanted to simplify this a little bit, we could combine the sine and the cosine. You might remember that sine divided by cosine is the tangent of theta. So this is g times the tangent of theta equals d squared over r. And so let's analyze this formula a little bit. We're going to rearrange it and put it in kind of an optimum form, but it basically relates the velocity of the car, the angle, and the radius of the track. Now, this would be how fast you would go if there's no friction at all. So if this ramp is straight, that is, the angle's not changing. If it were kind of a curving ramp, then the angle could change. If the angle doesn't change and we speed it up, then r has to get bigger because the left-hand side is constant. If v increases, r increases. If v decreases, r decreases. So with no friction at all, you can drive around this track at a certain speed. And if you want to, let's say you want to pass someone, you can hit the gas a little bit. Your r will slide up a little. You'll be at a bigger r than them. And then you can slow down and pass them. So you could actually make this a workable road system with no friction at all. And in a few minutes, we'll do an example with some numbers and see how fast you can go with this system. It's not a great system, but it works. And ordinarily, though, what we would do instead with this equation is we would rearrange it and solve for theta, and that would basically be our way of figuring out what angle we should build our road at so that we can drive around curves without relying on friction, so that if the road gets slick or something, we don't slide off of the road. So let's rearrange this and solve for theta. So we have tangent of theta equals v squared over r times g. And then to get the theta by itself, we take the inverse tangent of both sides. And this angle is known as the ideal banking angle. I should give that a capital A. This is a title. Ideal banking angle. So the idea is, suppose we make a road and the radius is 30 meters and we want to be able to travel around it at 20 meters per second. What angle would we need? So let's try that out. So we're going to find the ideal banking angle for a 30 meter radius curve with speed 20 meters per second. So we've got this road, we've got an angle that we want to discover, and the radius r equals 30 meters. So our angle is the inverse tangent of v squared over, now I'm putting a capital R because in my picture that's what I call the radius. And that would be the inverse tangent of 20 squared over 30 times 9.8. And it's getting out the calculator. I get 53.7 degrees. So that's quite a steep slope. And 20 meters per second is not so fast. So this clearly is not something we can do. We can't really build roads at this angle and expect cars to drive around, at this magic speed. At this angle, if your car stopped on the road, it would start to slide down the ramp. So, so instead, though, of course, we really do have friction, and when we combine friction with the effect of the normal force giving us an additional centripetal force, then we are able to actually get something. Okay, so any questions about this last example? Tommy. Tommy, I can't hear you if you're talking. Are you talking?
Hey, Professor, what is the number that you had in the numerator that's up there when you
Up
were
here?
doing the?
Yeah,
Say it
that's
again.
20 squared.
It's 20 squared. Okay.
Yeah, let me rewrite that.
Okay. Okay, I got you now. All right, cool.
Okay, good. Any other questions? All right. So let's see what happens when we try to add friction into that example. So I'm going to make the picture of the ramp bigger here. And so our car, one car, okay, so there's our car. And the forces now, if we want to solve, and what we're going to do, I'll give some numbers here in a minute, but we're going to solve for the maximum speed the car can go around a certain track with a certain radius with a certain amount of friction. Now, which way should the friction vector point? This is often a source of confusion. I could see a lot of different answers for this. The friction might point forward because you need friction to speed up, or it might point backward because friction slows you down. It could point up the ramp to keep you from sliding down the ramp, or it could be pointing down the ramp to keep you from sliding off if you go too fast. And technically, all of those are possible depending on the scenario. So if I just park the car on the ramp, then the friction will be pointing uphill, like that, because the car wants to slide down the ramp. If I'm driving around but I hit the brakes, the friction is going to point kind of back into the pitch in a way that I can't really draw very easily, but to slow the car down and stop it. If the car is at rest and starts speeding up on a hillside like that, then the friction will be forward. But we're talking about a car going around a ramp at a constant speed, okay? And the constant speed, we want it to be as fast as possible because we're looking for the maximum speed. So that means the car has exceeded that, the magic speed given by this formula. If we had no friction at all, there would be a certain speed for a certain angle and certain radius that the car could go without friction. And if we exceed that speed, then the radius wants to go up, okay? So we're imagining we're in that scenario, and the radius wants to go up, but the friction is keeping that from happening. And that means our friction is going to point down the ramp. Okay, so I know that's very tricky logic, but that's what's happening in this scenario because we're looking for the max speed. Okay, we're going to find the max. And after we find Vmax, I'm going to announce an extra credit opportunity where we do the opposite. We try to find the minimum speed this car can go around the track without sliding off. So pay special attention to this example, and then that will help you when I discuss the extra credit opportunity. Okay, so there are my three forces. And we're going to find Vmax if the radius of the track equals 30 meters. I like that radius. And mu static equals 1. That's if we have good tires. That's what mu static we would have. And theta equals, let's say, 20 degrees. Okay, so that's what we're after. And we have to remember that the center circle, we imagine this thing is going around, like that. And so the center of the circle is a point in space, just kind of hanging. So we want to split our vectors into not down the ramp and perpendicular to the ramp components, but regular old horizontal and vertical components. Okay, so that's how we do it. This will be NY, and this is NC. And then we have a friction Y and a friction C. So those are my forces. I've got the diagram correctly. We have only one point of contact, so we have only two forces, those forces being force of gravity and contact. And remember, friction plus normal counts as one force of contact. And now we're ready to write down Newton's second law. We have net force equals ma. We're going to have the centripetal components and the y components. And in the centripetal direction, we have n centripetal and friction centripetal, and we have to figure out the signs of these guys. So the normal force components, the y component points upward, and the c component points toward the center. For the friction, the c component points toward the center, and the y component points downward. So both of the c components point toward the center, so they're both going to get plus signs. Now, how about the angles? The angles, like you on the last example, I would show you that this angle is the same as that one. And so I'm going to do that by reminding you that when we were tilting the paper, we were breaking gravity into components. We're not breaking gravity into components today for this, but I want to remind you of that. When we did that, we saw that whatever this angle is, this angle would be the same angle. And whatever this angle is, that is exactly opposite to this angle. So this must also be 20 degrees up here. Okay, so that's the idea, and that always works that way. So to find the centripetal component of the normal force, again, it's opposite to the angle, so it's going to be n times the sine of theta. And for friction, we get the same, whatever this 20-degree angle is here, that's going to be the same as the angle at the left of the friction triangle. So FC is adjacent to that. We're going to get F times the cosine of theta equals m times v squared over r. And we know that friction is mu times normal, so this is normal sine of theta plus mu static normal cosine of theta, and that's equal to m v squared over r. We can even factor out the normal force here, looking ahead to the fact that we're going to have to substitute the normal force out of our equation at the end of the day. So the question is, just like before, we know theta, and we know mu, and we know r. We don't know the mass. I'm hoping it will cancel. But normal force, we got to find the normal force. This is common theme. So we go to the y equation, and we have 1, 2, 3 normal y, fy, fg, 3 y components. So we have ny, little fy, and fgy equals m times ay. But as usual, ay is 0 because the car moves in a horizontal circle. It's not going to move up or down. We have to get our sign, so the normal force points upward, but both friction and gravity point down. Then we do our components. The ny is just n times the cosine of theta. And the friction y, it's opposite to the angle, so it's f times the sine of theta. And the force of gravity y component, it's already its own y component. There's no horizontal or centripetal piece, so this is just Fg. And like before, we know the friction force is related to normal force, so we're going to replace the friction with mu static normal. And we'll move the force of gravity to the other side, and we recall that force of gravity, the formula for that is m times g. So we can factor out the normal force. And solve for it. And notice that once again, the normal force is totally different from in all of our other examples. So you really cannot just use the force to find the normal force. You have to work it out. So some of you didn't do well exactly, but you managed to kind of muddle through the contest without really being, writing these equations consistently. And I was, I think, fairly generous on taking off points there. But you're going to keep losing points on these kind of issues if you don't learn how to really do this the proper way. So here's our most complicated normal force we've ever seen, mg over cosine of theta minus mu static sine of theta. And we have to insert that in our left equation where the normal is. And this is going to give us, just one heck of a ugly equation. Mg over cosine of theta minus mu static sine of theta times sine of theta plus mu static cosine of theta. All of that stuff equals m times v squared over r. And I really cannot simplify this too much, other than to notice that both sides have an m, and all of this stuff is multiplied together, so the m is sort of multiplying everything on the left, and it's also multiplying everything on the right, and so therefore it just cancels. So I want to try to solve for v squared. I'm going to multiply both sides by r. That's going to give me r times g times sine of theta plus mu static cosine of theta. And I'm just going to move this denominator underneath the whole thing. Kind of imagine extending that line. Or in other words, these two things were multiplying together into the numerator. And so we have cosine of theta minus mu static sine of theta. So that's our expression for v squared. Of course, we want to take the square root of both sides. So v, in our example, is going to be the square root of all of that stuff. And here I'm going to put my numbers in. Our r is 30. G is 9.8. Then we have the sine of 20 plus 1 times the cosine of 20. All of that's on top, and then we have cosine of 20 minus 1 times the sine of 20. Let's see what kind of number I get out of that. Sorry, having a little trouble with my calculator here. Okay, I got, let me use a different color here. 25.1 meters per second. So I do not recall what we got when we did this example last time. Let's see, 1 times 30 times 9.8. So that was 17.1 meters per second. So we're comparing the same size track. If I give it a 20-degree angle, our maximum speed goes from 17 up to 25 meters per second. And this is why when you're driving on the highway and you go around a ramp, you notice that the ramp is always banked, meaning it's slanted in such a way that you're leaning into the curve. The normal force points into the curve. And every once in a while you'll see or be on a road where it's not banked properly. And one example of that is the parking lot at the Forest Park campus where I normally teach. There is, when you turn in off of Oakland, the very first left turn you make, it's actually sloped the wrong way. And the first year that I taught there, and it also says speed limit 10 miles per hour, which is like virtually impossible to go that slowly. The first year I was there, like we got a sprinkle of snow in the winter, and I tried to go around that curve at probably like 20 miles per hour, and I just slid right off of it because it was actually sloped the wrong way, so the normal force was pointing away from the center. Cost me like $500 because it bent some stuff up underneath my car, so I'm still a little bitter about that. Okay, so this is clearly, this expression is a very, very complicated expression. This is not something you're going to arrive at by just winging it. Okay, you're not going to get something like this by winging it. You really need to get your system down, and again, bravo, many of you really have it down. It's very, you know, great. It's great that a lot of you have it, and others, I'm seeing great improvement. You know, I'm seeing improvement. So if you're one of those who's improving, that's good. Keep at it. Keep working with me. You can collaborate, and I think you'll continue to improve. But if you haven't really been, if you are one of the ones who's just trying to look at the questions the day before the test and try to like mimic them without really understanding them, this is going to get worse for you, and you gotta try to work on a daily basis and work sort of systematically. So, are there any questions about this this example? Okay, so for extra credit, I will put this assignment up later today on Blackboard as, you know, an assignment that you can submit to. But you're going to find an expression for the minimum velocity that you can go. So let me go back to this picture. This was the way the forces look when we're doing the maximum velocity. But if you're doing the minimum velocity, basically, if you go the speed indicated by this equation, okay, based on the angle and radius that you have, if you go this speed, you don't need any friction. If you go above that speed, then the friction kicks in downhill to keep you from sliding up. On the other hand, if you go below that magic speed, then the friction, it's going to turn around and it's going to point up the ramp instead of down the ramp. And so your job for the extra credit is to repeat this with the friction pointing up the ramp instead of down the ramp. You're going to repeat this whole example and come up with an expression that looks something like this. You know, v equals the square root of some stuff, but it's not going to be exactly the same stuff. Okay, are there any questions about the extra credit? Okay, so I want to do one more example of this type of thing before we take a break. And then after the break, we're going to talk about gravity, which hopefully will connect with what you guys did on your orbits and gravity lab. So, okay, this last problem that I want to do, I want to imagine that we have like a tall pole. Oh, I'm going to do that again in black. So we have a tall pole, and no. Okay, there it is. There's my pole. And on the pole, we are going to tie a rope, and we're going to have a ball at the end of the rope. This is like tetherball. Raise your hand if you ever played tetherball when you were a kid. Okay, a lot of you. Raise your hand if you ever played tetherball as an adult. Oh, good for you. Is that a thing now? I miss tetherball. That should totally be an adult game. Okay. So in tetherball, you hit the ball and it's going to go a certain velocity, v. Okay. So now normally in tetherball, if you're any good at tetherball, then you know the circle is going to look kind of like that, so that the other person can't get the ball because they're too short, right? But we're going to imagine that the circle is just horizontal. Okay, so we hit this thing and it's going in a horizontal circle, which of course you can do, but it's not necessarily the best. Tommy, or do you have a question, or just still have your hand up from tetherball? Okay. All right. So what I would like to do is find the tension when the velocity is 20 meters per second. And suppose there is, you know, the length of this thing is 1.5 meters. Okay? So there's going to be a radius to the circle here, which depends on L and depends on this angle at the top. Okay? But we need to get our forces in the picture in order to solve this. So we have the force of gravity, which points, you know, downward. And then we have tension in the rope, which is making contact with the ball, but that's the only contact, because we're imagining we already hit it, and now it's just flying around in a circle. So those are the only two forces. And when we do sum of the forces equals ma, we're going to split this, again, into centripetal and y components. So the centripetal component looks like it's really just t. And if we draw the components in, we might draw them like that and like that. Not very good. Maybe so we have a ty and a tc, and then t is just there. And the angle, whatever's the angle at the top here, that's the same angle in the triangle for the tension. So we're going to have TC equals M times AC, and the tension centripetal component gets a plus sign because it does point toward the center of the circle. And then in the y direction, we're going to have Ty minus Fg equals 0. That's going to be T times the cosine of theta equals M times G. And on the left-hand side, we're going to have T times, oh, and we need to know the mass of the ball too. Sorry, I forgot to tell that. Suppose that's 1.3 kilograms. We're going to have T times the sine of theta equals M times V squared over R. Okay, so we want to solve for the tension. Well, let's see what we know. We know V, and we know the mass, M times G. And what we don't know is T or the angle. Okay, we don't know T or the angle. So let's remember that the R is related to the length and the angle. So we can rewrite this as T sine theta equals mv squared over L times the sine of theta. Actually, I think I gave the wrong information in this problem. Now that I'm looking at it, we need to be given the angle and solve for t and v, because it's difficult to solve for the angle in this case. So suppose we want to know when the angle is 30 degrees, so we're going to find t and v. Okay, so we're okay. Now what's given, what we know is the angle, the mass, L, and theta. And what we have to solve for, our unknowns, are t and v. Sorry about that. So we can use the y equation to solve directly for t. This is mg over cosine of theta. And since we want t by, we want it anyway, we can put our numbers in 1.3 times 9.8 over the cosine of 30. Okay, so that is 14.71 meters. Sorry, newtons, not meters. Okay. So once we have t, we can rearrange this to solve for v squared. V squared will be L t sine squared of theta over the mass. So v will be the square root of 1.5 times 14.71 times sine squared of 30 degrees over 1.3. and it's going to be 2.06 meters per second. Okay, any questions so far? Christian?
So at what point does the sine of theta get squared? I kind of missed like when that into the equation.
Yeah, that's a good question. So when right from here to here, we have a sine of theta on the left, and we have a sine of theta on the denominator of the right. So when I multiply that up, it becomes squared. Does that make sense?
Yes, thank you.
Okay, sure, great, good question. Any other questions? Okay, so let's kind of look at this expression just a little bit. We can see that as the as the angle increases, sine of small angles is small. So sine of 0 is 0, and sine of 90 is 1. So as the angle gets bigger, the velocity gets bigger. But let's also look at what happens to the tension. As the angle gets bigger, we're dividing by cosine of the angle, and as the angle gets bigger, cosine starts to approach 0. And when you're dividing by a very small number, you're getting a very big number. So the tension actually becomes bigger and bigger and bigger as that angle gets closer and closer to 90 degrees. And because the tension becomes big, the velocity becomes really big. So just for curiosity's sake, let's see what would have happened if our angle had been, say, 85 degrees instead of 30 degrees. So same problem. I'm just going to do it kind of in the side here. If the angle were 85 degrees, then T would be 1.3 times 9.8 divided by cosine of 85. And that is 147 newtons. 46. 146. So then the V is going to be the square root. It's getting a lot of lag here. Square root of 1.5 times 146 times the sine squared of 85 over 1.3. So the speed goes up to about 13 meters per second in this case. And as you can see, as that angle gets smaller, the tension's going to get bigger, and this velocity will get bigger. In fact, you can never reach 90 degrees. You could figure out at what angle this rope would break. Maybe your rope can only handle 1,000 newtons. And once you put in 1,000 newtons, we can solve for the angle and then see, how fast is it going. So there's a lot of kind of variations we could do with a problem like this. But the key is we get our forces, we sum the forces, and now we're splitting them into centripetal and Y. But this is otherwise very, very similar to what you've been doing in the last contest. Okay, so any last questions on this problem? Okay, well then let's go ahead and take a 5-minute break.